Okay, so we are wrapping up the topic of convolutional neural networks, which is chapter 9 of the Goodfellow Bengio deep learning textbook. And this second lecture is more of a research topic than the mainstream convolutional neural networks. So we got a sense for what is convolutional neural networks last time, where we use a kernel and followed by max pooling and so on. So that's how a CNN is designed. And CapsNets or capsule networks look at what is the shortcoming of the convolutional neural network and how can that be improved. So it's an idea for the future to saying this might be a better design. And what was this shortcoming of the convolutional neural network? Because there are some advantages by doing that. Instead of doing full set of matrix multiplications to go from one layer to the next layer, having a full set of weights corresponding to every interaction between the elements of one layer and the elements of the other layer, it reduces it to a smaller set of weights, a convolutional kernel, which is moved around on the earlier layer, which essentially boils down to a matrix with a whole bunch of zeros in it, and same values repeated again and again in the weight matrix. So shared values, so lesser computation. But there was another advantage that was provided by convolutional neural networks. For example, in the pooling function, when you have a max pool operation, you are replacing, let's say, a small region of 4 with one value, 4 with one value. So in a sense, it's and we said by doing that, what do you get by doing max pooling? One of which was it builds in some kind of a invariance to small changes in the input. We saw a small example where if we had a set of values here and we moved that to the right by just one place, by using a simple operation, you're changing the values significantly at the next level. By actually using max pooling operation, change is not as significant at the next level. Say, good. So if you want to get invariance to translation, then max pooling may be the way to do it. But that seems like a very low level type of function. Taking the max value gives you some invariance. It is not a very systematically or biologically thought out type of thing. How do we really achieve these invariances? And capsule networks attempt to do that in a more significant and intuitively satisfying way. So one advantage is achieving better invariance, or actually called equivariance, and also there are a few other advantages in terms of computation and other things we'll see. So that's not the only one. One is the primary one is the biological type of motivation. And constructing what are called as parse trees, that's another thing, is you would like to, when you go from one level to the next, you would like to have some kind of a tree structure imposed in terms of what object you're seeing. It does it in a more systematic way. So it promises a lot of improvements. So that's what this topic is about. And I believe it's a very nice direction neural networks are going in. So the outline of today's presentation is, as I mentioned, what are the limitations of convolutional neural networks? And they worked exceedingly well and commonly used. I guess if you're going to be an implementer of deep learning, you're going to be probably using convolutional neural networks in whatever you're going to be doing. Okay, if you're going to be a researcher wanting to see how I can do better than that, this here is a line of thinking. So, And here we define what is a capsule network. Essentially, we define a capsule network as consisting not of individual units. In a regular neural network, you have units in each layer. There's a set of units in one layer, set of units in another layer. Units get connected to from one layer to the next layer. And there are some weights associated to each of these connections. We multiply the values of the units, let's say starting with the inputs. We multiply these values. By these weights, we add them up. And then there is a activation function at that unit, which is a nonlinearity, which takes that summed, weighted sum as input and maps it to typically 0 to 1 if we're using sigmoid or some other variations such as ReLU, so on. So that's what happens in a regular neural network. In a capsule network, we we say that you are losing a lot of information when you go from one level to the next level. And particularly if in a convolutional neural network type of setup, where we're kind of removing lots of values, replacing by a single value, and there might be a lot of information that is useful from the lower levels that can be useful at an upper level. And you can think of what a standard neural network does. When you feed in these values, summed values, and do a 0 to 1 activation function, you're actually calculating a likelihood. It's calculating a value between 0 and 1. That's a probability. A likelihood is a probability. Saying based on all these inputs, I give you a probability. A high value or a low value indicates something associated with that set of features. That's exactly how logistic regression works. Logistic regression is a 0-1 function, two-class problem, 0-1. And what does it do? It takes all these inputs and figures out all the weights in logistic. I mean, you do it in a training part, which is going to be an iterative method to train the weights, whatever be the method. You figure this out, and what does logistic regression do? For this set of inputs, multiply by the weights, add them up, run it through a sigmoid function. That's what logistic regression does, which maps as a squashing function, which maps it into a 0-1. And if the value is 0.9, if the output is 0.9, it means there's 90% probability it is of the first class, 10% probability of the other class. So it's giving you a likelihood of what class this belongs to. What's the probability it belongs to that class? That's exactly what a particular unit does. And what is being argued here as a preamble to capsule networks is that all you're doing is calculating a probability and not retaining any of the lower level information that could be useful at the next stage. All you have is a strength. It seems like an arbitrary thing, and pass along some more information from one layer to the next layer. So it says instead of that single unit that computes a value between 0 and 1, replace it by what's called as a capsule. And a capsule is an idea which says it encloses a number of units inside it. So that's all it is. Instead of being a scalar value, an ordinary neuron gives you a scalar value, right? It's a mapping. Whereas a capsule gives you a vector value as output. So such a simple transformation. It is going from a scalar value to a vector value at each node. And that vector value feeds into another vector value at the next level. That's all it is. So instead of showing it as circles for units, we show it like a oval shape, something like a capsule of medicine, right? A tablet of a capsule we have. That capsule has inside it some tablets, or right, like that. So it's the same idea. So we have, instead of a scalar value, we have a vector value inside the capsule. And what do all these these values, or the elements of this vector, what do they represent? Some of which can be used to calculate the probability again, just like an ordinary neuron. Like if instead of giving a, let's say the capsule had only 2 elements in it. It has two elements. It means it's a vector in two-dimensional space. Vector in two-dimensional space, you can calculate its magnitude and direction, right? If I give you a vector x with values x1 and x2, immediately you can say, well, if you give me two values, I can tell you what is the magnitude of this vector and what is the direction of this vector. The magnitude would be what? X1 and x2 are the two elements. The magnitude of a vector is square root of x1 squared plus x2 squared is the magnitude of the vector. What is the length of that vector in the two-dimensional space? X1 squared plus x2 squared. And the direction is the angle that that vector makes with the x-axis, right? If I say a vector is 3, 4, 3, 4, and it's a point 3 along x and 4 along y, so that's that point, and its magnitude is square root of 3 squared plus 4 squared, which is 9 plus 16, 25. Square root of that is exactly 5, right? So the length of that vector is 5. When I say 3, 4, length of it is 5, and the angle is tan inverse y by x, right? Tan inverse y by x. That is tan inverse 4 by 3, 4 divided by 3, which is some angle, right? Tan inverse. You can look up in a table saying, what is the tan inverse? What is tan inverse of infinity? Pi by 2. Yeah. So tan inverse of infinity is pi by 2. Tan is sine over cos, right? The inverse of it we're talking. So if the so it's tan inverse of infinity means the vector is perfectly perpendicular and going in the y direction. Then we say the angle of that is 90 degrees from the x-axis, pi by 2, right? Tan inverse of 4 divided by 3 is some other angle between 0 and 90 degrees. 0 and 90 degrees. Probably more in the middle. Okay, so the capsule can have two values. Together they represent the magnitude and the direction. The magnitude can be interpreted as, again, a likelihood. Just like a neuron would give you a value, a probability, a vector can also give you a probability by calculating the magnitude. But it's also telling you something more. Not only the probability, it's also telling you something about the orientation of the object also, maybe, the direction. Something more is being carried by having two values. By having three values, you could have something even more about the quality of the input, right? We can define these things like that. So that's the definition of capsule is that. And then there's a very interesting idea called dynamic routing or routing, they call it. The dynamic routing is how values get transmitted from one layer to the next layer, not just based on a matrix multiplication, which is all the weights are learned by backward propagation, but also something that is done dynamically based on what is the input. So if you think about the pooling operation in convolutional neural network, normally we multiply between two layers just by a matrix to go from one layer to the next layer. But with pooling, I mean, those are all determined ahead of time. The weights are determined during back propagation, during training time, you figure out the weights. During the performance stage of the neural network in forward propagation, we know the weights, we just multiply it, that's it. Max pooling does something a little bit different. It says the values at the next layer are not going to be just dependent upon the values learned ahead of time, but it also depends on what is the input you gave me. Because it takes these values, and then you take a max of a bunch of them. And that is what's being transmitted. So when you have a pooling layer, there is some dependency on the input and not just on the pre-trained weights. So you can say there is a level of dynamics going on there, in the sense it's not static. Static would be predetermined. Dynamic would be depends on what you input, and it adjusts to that and provides the next value. This is what capsule nets do. It's saying why should it be just maximum? We can define something more sophisticated than that. And so it uses not only the weights, but also what are called as coupling coefficients to go from one layer to the next layer. Cij, they refer to. From the ith level to the jth level. What is ith level of not units, but ith level of capsules to the jth level of capsules. It figures out a routing coefficient between the two. And then there are all kinds of details. Computing input-output vectors of a capsule. Because we're talking about input-output. Input is a vector coming in. Because all capsule, capsule, capsule. So you have input-output vectors of a capsule. And then the routing by agreement. So this involves a little learning again. We know all about backpropagation. That is all the weights to be determined left to right, backpropagate based on gradient descent. We figure that out, right? That's what standard neural network is. Capsule networks say, in addition to all this backpropagation, we also need to figure out how a capsule feeds to the next level. And in a way, the Cij, these are called the coefficients, routing coefficients. Those are determined by how in the beginning they're all kind of equally weighted. But it says some of these seem to be more in agreement than the others. So we calculate that value after a few passes, figure out the right coupling coefficients. So there is something more dynamic happening, much more happening than in an ordinary neural network. And then there is a CapsNet architecture. How do you put it all together to solve a problem, right? And then we can talk about how well does it perform, right? How does a CapsNet perform? And then there are other new research topics. This is another very current topic, matrix capsules with expectation maximization, an old topic in introductory machine learning that also plays a role. So I'm giving you the big picture here. There's a lot to study here. And again, even in the mainstream of deep learning, we've been seeing that there are a number of things we don't have very good answers for. Thinking, well, that's it. This is what people know so far about it. Here, we know even less, but it's kind of an exciting direction, I think. You can't simply run it head to head. How does an ordinary neural network do? How does a capsule network do? You might find out the regular neural network with CNN does better by that, because you might be using some simple problem where that is all you need to solve the problem. But we're talking about something to advance the state of the art, saying it seems so silly to do max operation and expect it to be very powerful with a CNN. There's got to be more to it than that. And so we again begin this discussion with the biological inspiration to some extent. We said deep learning is all about that, biologically inspired approaches to multi-layer machine learning. So there is some such motivation here also. So this slide is nothing new. I just showed this diagram last time also. And in a convolutional network, what do we do? We minimize computation compared to a regular neural network. Convolution simplifies the computation to a great extent without losing the essence of the data. It simplifies the computation. And they are great at handling image classification. They use the same knowledge across all image locations. So on here's a picture of a car, here's a convolution plus a ReLU, there's pooling, this is an important part. This is the part we're replacing with. They're saying pooling should be replaced with dynamic routing, we call it. There's some dynamism here. Pooling also is dynamic in that it selects the value that is maximum and then takes it along here. So we're saying that we're going to make it a little more sophisticated. So convolution ReLU pooling, and then there is the standard. So this is standard convolutional neural network. So you see, in a convolutional neural network, given an input image, a set of kernels or filters scan it and perform the convolution operation. It's not just one kernel we use. We can use several kernels. Some of them we saw some examples, 64 kernels and so on. So it creates, and this creates a feature map inside, and they pass along via activation pooling layers. Activation layers introduce nonlinearity. Reducing the training time. Well, pooling creates summaries of each. So there are two things happening with pooling. Pooling creates summaries of each subregion and helps invariance to transformation. Both of them. It's really for free. You are reducing the amount of computation and also getting some invariance. It's more robust. And then at the end, it will pass via a classifier using sigmoid for a two-class classifier, softmax for a multi-class classifier. And the training is based on backpropagation of error matched against the labeled data. And nonlinearity also solves the vanishing gradient problem. The nonlinearity that is brought in by activation functions. I just threw this slide in here. We saw it last time. How does pooling create invariance? And we have a detector stage and a pooling stage. And for an input, we're just taking the max of all these values, right? The max of 0.1 and 0.2 is 0.2, max of 0.1, 1 and 0.2 is 1, like that. And then we translate the input here by 1 at the bottom row. We introduce this 0.3 here. There is the same 0.1, 1, 0.2, and the output gets changed. And we notice that although all the input elements got changed here, only some of the outputs got changed, saying, oh, okay, there is a little bit of robustness towards moving it by 1. The image may look quite different at a low level, but at the upper level, there is some stability there, even though all the values got changed by moving to the right. But then we say, it's a very crude approach. So simply, reveling on the fact that just moved it a little bit, changed more or less, and it in reality it removes all sorts of positional invariance. So it's not a very nice approach. It does, to some extent, it does something for free. Now here is a classic example of how a CNN can go really wrong. A CNN is capturing features and going on to the next stage. And for instance, you might be able to say, what is this thing? It's recognized as a face. Whereas we have here is a version of the face done by a modern artist like Salvador Dali or somebody, and feed that to a convolutional neural network. Locally, it might detect all this eye is here and mouth is here and eye is here. I guess it's a nose is here and so on. But that also can get recognized as a face because it's just calculating the presence of these things and some probability associated with them. And then it's putting it together at the next stage, saying, okay, I got all these values for all of these, so it must be a face. And what is lacking here is an awareness of the relative positioning of these objects, because you're passing along some filters and it is capturing the presence. One filter may capture the eye, the other filter may capture something, and so on. It's present, 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 and uh, and so you're getting something nonsensical here. Maybe if you're a Dali fan, you might not think it is nonsensical. All right. So CapsNets are an improvement on CNNs, and they are the next version of CNNs, and they solve problems due to max pooling and deep nets. Loss of information regarding order and feature orientation. Jeffrey Hinton, who proposed the CapsNets, said the pooling operation used in CNNs is a big mistake, and the fact that it so works so well is a disaster. Right? It's become the mainstream learning convolutional neural networks. So the solution offered by Capsule networks is a low-level feature should also be arranged in a certain order for the object to be classified as a face. Somehow ordering information has to come into play. And order is determined during training when the network learns not only what features to look for, but also what their relationships to one another should be. Seems like a very obvious thing to say, but that's not how these deep learning networks have been working. They detect features and then you put it together. Features are all present, so it's got to be this. What is the relationship? Learn that nose is between eyes and mouth below that, right? It's in between the eyes and the mouth, and it's below them. And images that have features in that particular order will then be classified as face. Everything else is rejected. So a Salvador Dali picture should be rejected rather than accepted as a face. Okay, here is some of the inspiration from biology. Knew this, that the human vision uses what's called saccades. You in the past, I've been working on machines that can read and so on, right? OCR and these kinds of things. But we had studied long ago. Psychologists knew that when human beings read text, we don't go across like a scanner, going left to right. That's not how the human eye reads text left to right. What we do is we fixate on one point, and at that fixation point, we are clearly seeing what is there. And then we are seeing in the periphery of our eye what is next to it on either side. It's kind of a very slightly vague form. It's not as clear an image in the eye. And then we don't necessarily go on to the next point, next point, next point. That's not how the human vision system works. If you fixate on one point, you get a rough idea of what's next to it, and we move to a later point, fixate again, and we again get a rough idea of what is next to it. So these are called saccades. And this has been shown by conducting experiments on humans on some kind of a screen to see how somebody's asked to read something, and we're fixating like that. And a proof of why that is that we do that is reading for understanding versus reading for finding typographical errors. Sometimes when we are reading text, we don't catch a typographical error because we're just going along and we're reading for comprehension, so on. But if you were to proofread your document for publication or something, and now you have to read it very carefully, you have to fixate, because some shapes of some letters, you might unconsciously assume that it is right and you move on. Because we are predicting actually. What is happening is we're not clearly seeing some of the letters, but when we see some letters, our vocabulary is predicting what the next one should be. And it can be wrong, but still it's assuming it is right. So that's why we don't catch it. And so So our eye and comprehension is different from OCR, which is trying to recognize every character. What is this, right? So these are, I think I took this from one of Jeff Hinton's paper. He gives a lot of uh, importance to this idea. This is about the Saccards. When we're reading market a new bike, the bike was ready. If you're just reading like that, we miss out if there are any mistakes and so on. But anyway, this is how the Saccards work, and kind of moving along. And yes, it's even slanted here. And when we look at that's with the text. But even when we look at a photograph, it shows the Saccards here. Somebody staring at this photograph. The eyesight is kind of moving along to the key points. All right. So what are they saying here? Is human vision uses Saccards, ignores irrelevant details by a careful sequence of fixations, and ensures only a tiny fraction of the optic array is ever processed at a highest resolution. Very little of the image is processed at high resolution. And we assume that a single fixation will give much more than a single identified object and its properties. When we fixate on this, it's not just one word we are reading, but we are also getting some information next to it. So assume that a multi-layer visual system creates a parse tree on each fixation, and we ignore the coordination of parse trees over multiple fixations. So we have some sense of what is the high-level object, what are the sub-level objects. So even with one fixation, we get some idea of the whole thing. And what do you mean by parse tree? So this is about parsing a natural scene image. So this says, what is this image here? And that image consists of some grass and people and a building and a tree. So we can say this is a scene of a grass, people, building, and tree. And grass has some subpart to it, people has some subpart to it. They're all images. And then the building is subpart to it. And the building itself is a complicated building. It's got a roof and walls and the door and all that. So on. So there is this semantic representation of features and segments. Similarly, a natural language sentence, this corresponds to the description of that. A small crowd quietly enters the historic church. And again, you have subject, noun, phrase, verb phrase, and so on. A small crowd is a noun phrase, quietly enters a verb phrase, and this is the historic church with a determiner, adjective, and a noun. So we say this is what's meant by a parse tree of a sentence, and we have a parse tree of an image. So what Jeffrey Hinton says here that when we look at that image, there is some kind of a parse tree with even one fixation that's being created of more than just that point, but including the surrounding regions. So there is a structure to it. So how do we capture this idea of a parse tree? And which is why he says we need more information than one element. So parse tree for a fixation. For a single fixation, a parse tree is carved out of a fixed multi-layer neural network, like a sculpture from a rock. So we have a neural network, maybe for buildings or something, sentences designed, standard neural network, but at dynamic time, that we have this neural network, but there is some kind of a structure to it, substructure to it, which is like a parse tree. Each layer will be divided into many small groups of neurons called capsules. And each node in the parse tree will correspond to an active capsule. So he's doing multiple things here. One is changing the neuron to a capsule, and also talking about some part of the neural network which captures the information like a parse tree. So there are two different things going on here. First one is easy to understand, which is replaced by a scalar by a vector. Okay, that's easy. But this thing about constructing a parse tree is a little more involved with the routing and all that. Here again, another attempt to explain this. So activation is a likelihood. It's an interesting idea. The activation level of a neuron can be interpreted as a likelihood of detecting a specific feature. Here is a US school bus. US school buses are always painted yellow, I suppose, purposely so that it's very bright and somebody does not cause an accident to it. Here is some deep learning network which has to classify whether it's a school bus or it's an airplane. And we have a high activation if the neuron detects the image contains a lot of yellow color. We have said earlier on that in deep learning we have layers to layers to layers. It's learning some features as we move on. And finally, we have a classification when it's captured certain good features, simplifies the problem, and we can have a simple linear classifier at the last stage. So it could be that a neuron like that says, I have a high probability of yellow happening here. Right? So we're saying it is that neuron is calculating the likelihood of yellow color. So we're now saying that is the idea that we were generalizing. The capsule is a group of neurons that not only capture the likelihood, but also the parameters of the specific feature. It could be something more about the parameter. I guess I don't know what the parameters for yellow could be. Right? Yellow in a long yellow thing or something, some parameters. So all we are saying is that neuron, that individual neuron here, is now being replaced by a capsule, which is shown like a picture of a capsule with a couple of neurons inside it. So we do this comparison of the two quite a bit. CNN versus CapsNets or capsule networks. So artificial neurons traditionally output a scalar real valued activation that loosely represents the probability of an observation, that particular feature. CNN is scalar in nature, that way it's a scalar value, probability. Max pool layers just try to get important information from the images, but use structural orientation of those features. So it's kind of doing a crude operation. Due to which at higher levels, CNN only checks whether the feature is present or not, irrespective of position they are in. So in that sense, similar to bag of words in natural language processing, you might be familiar with a basic method for NLP, natural language processing. If given a sentence, it just the bag of words thinks of it as not as a structured sentence, but as if each word has been thrown into a bag in a jumble, and it simply tells you which words are present and how many times it is present. Also could be there in a bag of words, but doesn't say anything about which word goes next to which word, right? Which reminds me, in English, it's extremely important, right? To say what is the order of these words in the sentence. Meaning can be completely changed if you move the words around in a sentence. But I believe in Sanskrit, that is not the case. You can have the same sentence with any word put anywhere else without changing the meaning. You may want to look into that, whether that's really true, right? And why is that possible in Sanskrit without changing the meaning? Is because the word has a certain word ending, right? Vibhakti or something like that, which kind of uniquely identifies these things. So you can have a sentence. I don't think it's true of all Indian languages. I think it's true of Sanskrit, which has that property where they formally defined all the vibhaktis and right? The parsing of the, and also the conjugation of the verbs, right? You have all the verbs in Sanskrit, and then you have conjugations of them. The conjugations involve, like, is it a verb applied to one person or two people or three people? So uniquely, that word tells you how many people are there, and so on. So there is that property if one could do that. But when we're talking about here, we're talking about English language, where that is, maybe in Sanskrit also there might be situations where there might be ambiguity if the words are interchanged. Case. But when it becomes bag of words, you can still do some useful things with it, but it has lost syntax, right, and semantics, so on. So we are arguing here. The same thing is happening with CNN. It's got the eyes and the nose, everything coming in and saying we lost track of which goes where, and still we are saying it's a face. So CapNets replace scalar output feature detectors with vector output capsules and max pooling with, so two things happening, as I said, we're getting capsules and then we're also getting routing by agreement. So again, a definition of a capsule is a group of neurons whose outputs represent different properties of the same entity. And a capsule is a group of neurons whose activity vector represents the instantiation parameters, a specific type of entity, such as object or object part. So it has got, you have instantiated it, you've got a particular image of a school bus, and we have the instantiation parameters. So here's a more concrete example with handwritten digits, right? Most research in AI, machine learning, deep learning, etc., they begin with handwritten digits as a starting point. And if we had a conventional neural network, on the top you have the handwritten digit 7 and a single neuron, an output for that image of 7 coming out as, for a 7, it's a 0.9. It's saying the probability of that being a 7 is 0.9. It's some sort of pixel values coming in and it figures out the weights, or we have some features computed from the pixel values. Output is, we have got maybe a softmax output, 0 through 9. And the detector number 7 is saying that's a 0.9 for a 7, and the rest are all adding up to 0.1. So that's a conventional neural. In a capsule network, we don't have a single neuron, but we have a capsule of 2. And this one, when you have a capsule of 2, like the output is a vector now, it could be like vector is equal to 0 and 0.9, two values. Where we've chosen that nicely that the magnitude of that vector V is square root of 0 plus 0.81, which is square of 0.9. And square root of that is equal to 0.9 is a probability. Okay, so we got the same information that the probability of 7 is 0.9. And we are also able to calculate the direction. We're saying there is a vector here, which is a vector of two values, 0 and 0.9. 0 along the x-axis and 0.9 along the y-axis. What does that mean? What is the angle of this to the x-axis? And the direction is tan inverse of 0.9 divided by 0, which is equal to tan inverse of infinity, which is equal to pi by 2. That's why I asked this question, 90 degrees, right? So it is saying when you got that value, it is a vector of that form. And let's say if that same digit was rotated to the right a little bit, the output could be a vector like this, saying the output vector is 0.1, 0.84. It has about the same magnitude of 0.9. It is almost as sure that it's this, except you are also getting some direction is 83 degrees instead of 90 degrees is this, right? 90 degrees. For a moment, I was just thinking, yeah. Yeah. Yeah, this is I suppose it's fixed prior. It is just illustrating that there can be more information contained, and one of which could be the probability, and the other one could be the rotation by so many degrees. Yeah, you could. I suppose we could train it in a very conventional way, and you would, let's say in supervised learning, you would kind of give that information. How much rotation there is, capture it by another neuron. You could do it like that, right? Yeah, yeah, different things. My next slide actually shows that. This one here, or maybe the one after. Uh, so we're saying there can be some way of capturing more information than just the probability. That can be a value. Like, let's say this 7, it is not as clear that it's a 7. A neuron could say zero point 0.3. Says, I got confidence of 0.3, that's a 7. A capsule again produces a short vector, a lower magnitude probability. It captures the same idea. It has got a magnitude of zero point 0.3 and a direction which is again vertical. And we can say this one is a rotated version, again is zero point 0.3, but with a rotation here. So it's capturing two pieces of information. Your question was, can you capture more information? I think I lost it. Okay. No, I have it after this. Let me go to that slide first and come back. So this says, I could have 4 capsules. I mean, 4 units in a capsule, not 4 capsules. 4 units in a capsule. And that can capture, 2 of them we saw can capture the magnitude and direction. And you can have this one capturing the size, how big is the image. And this one captures the thickness of the stroke. So you see there are some 7s that are smaller than the others and some are thicker than the others. So we are passing along not just how much of a 7 it is, but also what kind of a 7 it is. This is a 4D capsule. Training it and all is a bit different issue. How do you train all these things? But this is saying somehow the capsule can contain more than confidence. Yeah. Hmm? Yeah. Yeah, I guess, yeah. Yeah, last layer. We might not, yeah. Yeah. So yeah, we have to go through that systematically to see how do you what is the architecture. Starting point is we need more information. Please code more information for me. All right, we're saying, well, this is how you would use it. Okay. How do you actually calculate it is a different issue. Okay. Let's just get a concept here, because there are lots of other details. So representing entity in input. Within an active capsule, its neurons represent various properties of an pose. We call it position, size, orientation, deformation, velocity, hue, texture. All these things could be the properties. All right, various properties. One special property is the existence of an instantiated entity in an image. I suppose that would be like the strength of a 7.7 or 0.9. And representing existence of an entity is by a separate logistic unit whose output is probability that entity exists. Length of the vector of instantiation parameters represents entity existence. So the length of the vector, if it is 0, it means it's not a 7. When it says the length is 0.9, it says, that's a pretty confident that's the length. Its orientation represents properties of the entity. So we ensure length of the vector output of a capsule cannot exceed 1 by applying a nonlinearity that leaves orientation unchanged but scales down its magnitude. Okay, there's some detail here we need to pay attention to about what kind of values are these. And this is a 4. Here is a nice, again, we're still trying to define what is the idea. And this says, I mean, this is a well known fact that computer vision is the inverse of computer graphics. In computer graphics, what do? We say, well, we want a rectangle of size 20 by 30, the angle is 16 degrees. Or we need a triangle of size 24 by 25, the angle is minus 65 degrees. In computer graphics, we go from this description, we go to what's called as rendering, and we say, well, those are the two objects you specified for me. In computer graphics, we're always specifying what is it you want to draw. That's called computer graphics. In computer vision, we do inverse graphics, and we look at this image and we say, what is this? So this is called inverse rendering, which says, well, that consists of a rectangle and a triangle. The rectangle is this one of this magnitude, and this is magnitude, right? So this is the two directions, rendering and inverse rendering. And so so the whole thing is, how do we get inverse rendering? And this is an idea. Capsule networks can help you. Like this is the image we are seeing, the same image. And out comes from this image some kind of a capsule level. So there is a capsule present in each location here. And each of them has idea of a rectangle and a triangle and what direction and what magnitude. Since this rectangle and this triangle are about in this location here, there's a very strong vector here and a strong vector. Blue corresponds to a triangle and the black corresponds to the rectangle. And there are weaker representations of these because there is a view of the whole thing from the entire image. The idea of this saccades we talked about. So there is a strength in each of these. There's a strong one over here. So there is a capsule present in each location, the input image. Each capsule has two vectors corresponding to the triangle, the rectangle. So this is kind of taking it to the next stage, saying what's going on here is the vectors are capturing this information. Right. Okay, there is so one of the TAs here today? No? Okay, so I'll keep going today. Anirban, are you here? Okay. Enough to be said about this topic, so we can use the extra time here. So this is again pooling and equivariance. So we talked about the idea of invariance is if I move it a little bit, the output should not change. If I rotate it a little bit, the output should not. It's still a 7. Still a 7. Unless I completely turn it upside down, in which case it becomes something else. Right? So that we call it as it's invariance to a transformation of rotation, translation, and affine transformations, we call it. And so pooling in a CNN is a very crude approach. In reality, it removes all sorts of position invariance and leads to detecting right image in figure 1 as a correct shape. Yeah, we have a disfiguration transformation. It's upside down here. And that's a proportional transformation. It's a disfiguration transformation. So equivariance makes network understand that rotation or proportion change and adapt itself according to that spatial position inside an image is not lost. So it needs to understand as to what kind of a change is happening. So let's say example of equivariance gaps. There's the same thing. There's a famous actual painting, Picasso's portrait of a woman, right? That is an actual painting of a person. And inspiring that, there is an input which, hey Anirban, are you here? I was just wondering whether I should go on or we will take over. What do you have in mind today? Hmm? Third project. All right. Okay, I was just telling the class that we'll continue to talk about capsule networks, and I think maybe third project is more important. Second project is over, right? Second project is done, so they need to work on third project, which is about recurrent neural networks. It's a totally different topic. So what did I not cover so far? We went over the idea of motivation for CapsNets. We went over how it attempts to solve two different problems of missing out on all kinds of information with pooling, and then the idea of a parse tree that's also comes into play. And I have a ton of slides on this topic. This is a topic that intrigued me as soon as Jeffrey Hinton came out with it. I think 2 years ago, he came out with this idea, and hundreds of bright people jumped on the problem, and there's a ton of papers already. One weird thing was he wrote a paper. He and his students wrote a paper on capsule networks, and it was going to be presented in 4 or 5 months later in a conference, and he put it on archives. Everybody jumped on that paper and already started implementing it, and they started getting results and analysis and saying, I can improve this to that and so on. So by the time the paper got published, there were like lots of other papers saying how they can improve that stuff. So his presentation of that paper had to not only deal with his paper, but what the others are saying and what improvements have come around. I guess that's the reality of today's world, because you put your paper on archive before the conference, and by the time of the conference, there is if it is an interesting topic, others will work on it immediately and see what kind of results they get out of it and know more about it than you do, because you only explored some aspects of it. So there is a lot on this thing. So I was also trying to do that 2 years ago, saying, okay, let me read some more papers on this topic. And so my slides were done before his paper was published. So I was lecturing to the class before the original paper was published. And it seemed to be a little dying down of interest on the topic, but I think it's still a very good idea, very good topic, very rich topic to do some research on. And so you'll have to follow up what all has happened. Why did it die off a little bit, and why did it pick up? And neural networks is full of this kind of history. Somebody proposes an idea, nobody believes in it, and it comes back again as the thing to do, right? So, but this seems to have all the potential of having some value. The dynamic routing is an interesting issue. What happens is, not only is there a matrix multiplication going on from one level to the next level, now you are going from one level of capsules to the next level of capsules. There is also some values going from whole capsule, one number is going, Cij is going from here to there. And that Cij is going to get changed dynamically in that it looks at all the values coming in and which one values are agreeing. If they're agreeing, then you strengthen the ones that are already there and weaken some of the others. So it tries to build a parse tree of saying, how does a parse tree go from here to here as opposed to all over? So it is a specific design called dynamic routing. You may want to take a look at it. We didn't create a project on it. Maybe in another version of this class, I might make this into a class project. Implement capsule networks.